Perfect, thank you.
So we're live.
Hello, everyone. Welcome to the Wikimedia Research Showcase for February 2022. My name is Martin Gerlach. I'm a research scientist at the Wikimedia Foundation. I'll be the host for today. The theme today is collective attention in Wikipedia. Collective attention typically denotes attention to items or novel items in large groups here in the context of Wikipedia and its readers. Just to give some numbers to put things into perspective, what large means is there are approximately 15 billion page views per month in all Wikipedia projects. And just in English Wikipedia, we have around 800 million unique devices per month. As our part, or as part of our program to address knowledge gaps, we are especially interested in understanding interests and motivations of our readers. And one way these interests and motivations show up is which content readers are choosing to visit. And of course, this is not independent of what is happening in the world. This can be readily seen by inspecting one of these various lists on the internet about most viewed articles in Wikipedia. Consistently throughout each year, it features pages especially related to elections, biographies, especially the article on the list of deaths of people in each year ranks very highly, sports events, or global pandemics that last for a very long time. And for the latter, especially, we have seen that there has been a huge shift in not just the number of readers and editors, but also the topics that readers are interested in. And to better understand these interactions and dynamics, we are very glad to have two excellent speakers today. I want to briefly introduce them. First, we have Renaud Lambiotte, and I hope I pronounced his name correctly, professor at the Mathematical Institute at University of Oxford. His main research interest is in modeling and analysis of processes taking place on large networks. He will talk about modeling collective anticipation and response on Wikipedia. In the second half, we will have Kristina Gligoric, PhD student in the data science lab at EPFL. And she will talk about sudden attention shifts on Wikipedia during the COVID-19 crisis. I want to thank both of them for being here, for taking the time and to share their research with us today. At the end of each talk, we'll have time for Q&A. So if you have questions for the speakers, please put them in the chat on YouTube or on IRC, and my colleague Emily will relay them to the speakers here. And before I hand it off to the speakers, I want to make two quick announcements. We have the 9th annual Wiki Workshop coming up, our largest research event of the year. As part of the Web Conference 2022, if you conduct research on Wikimedia projects, we encourage you to submit your ongoing or completed work. The submission deadline for non-archival papers is March 10. Please go to wikiworkshop.org. And together with collaborators, we are also hosting the first Wiki M3L workshop, a workshop about Wikipedia and multimodal and multilingual research. We invite you to join us at the workshop as part of the ICLR 2022 conference. Submissions of new and existing works around the usage of Wikipedia data for multimodal and multilingual machine learning are due on February 25. That's it from my side. I hand it off to Renaud. Thank you very much for joining us.
I think I can speak now. I hope you can hear me now. So first of all, thank you very much for the invitation, for the opportunity to present our research in this online venue. So I'm going to try to share my screen because I didn't try yet. And for some, okay, here it is. I'll share everything. And in principle, you should see it, I suppose. Yep. Is it okay for everyone?
Yes, we can see it.
Okay,
yes,
wonderful.
Perfect.
So Okay, so as I said, as was said just before by Martin. So I'm a mathematician. I work in the Math Institute in Oxford. By background, I was a physicist, so I've been transitioning from physics to more applied math for the last 15, 20 years. And today what I'm going to talk about is a paper that was done in collaboration with researchers in Japan, so mainly with Ryota Kobayashi, and with a researcher from the Math Institute, who's now at LSE in London, and his name is Patrick Gildersleeve. And the title of the talk is Modeling Collective Anticipation and Response on Wikipedia. So this paper has been presented and published at ICWSM, and you have a link here for the online version that you are very welcome to, that I invite you to download and to read, and don't hesitate to send us any comment if you have. So before I start, I just wanted to give you just a little bit of like a overview of the kind of research that I am interested in, and try to connect it more broadly speaking to questions that could be interesting to you before I go directly into the paper itself. So as I said, I'm a physicist. I'm also I turned applied mathematician. I tend to work with people from different disciplines, and well, I'm part of a community that calls itself people studying complex systems. And complex systems is a field of research that is usually quite difficult to define. And so here I just give you like one definition. It's as good as any others, I suppose, of what a complex system is. And so that's taken from the Encyclopedia of Complexity and System Science, where it says that complex systems consist of a large number of interacting components. The interactions give rise to emergent hierarchical structures, and the components of the system and properties at systems level typically change with time. So there are many complicated words here, but the most important is basically to keep in mind that a complex system is basically made of several elements that are basically that interact with each other. And due to their dynamical behavior, due to the interactions between a myriad and a very large number of components, you may have the emergence of non-trivial behaviors at the global scale. That would be at the collective level, basically. And basically, most of the research is interested in trying to understand how the behavior of all of the individual components together lead to collective behaviors. Now, unfortunately, it's the night here in Europe, so I cannot show you the beautiful sky that you would have in the UK. Of course, it's been raining, so I'm lying. But if it had been a blue sky, and if we could see birds flying together, well, the flock of birds is one of the canonical examples of what the complex system is. Why? Because you have that all of the birds fly together, right? All of them are influenced by the directions of the birds that are around them. And by the multitude of all of these interactions, you have the formation of these beautiful patterns in the sky. And basically, you have these key ingredients of having dynamics, of having interactions, of having many basically agents interacting with each other, and that together lead to these beautiful patterns that are spatial and dynamical at the same time. Now, among the types of tools that people use to analyze complex systems, well, there are agent-based models, you would have information theory, you would have dynamical systems, chaos theory. There's a lot these days of data mining, optimization, machine learning. But I am personally someone who's been working quite a lot on networks. So what would be my core research topic would be networks. I'm interested in anything that can be represented by graphs and networks. And what I find beautiful in networks is that they provide us with a language that is universal in a way, as soon as connectivity is the key aspect that you're interested in. And so it means that every time you have a system where you have components in interaction, and these interactions are critical to understand how the system functions, you can represent it and abstract it as a graph, as a network. We would have nodes and links, the nodes being the elements and the links being the pairwise connections. And here you have just two examples where on the left you would have a social network, on the right I think it's a protein interaction network. But the most important is to see that in both cases you can represent them with the same language, right? You can use the same algorithms to analyze them, and yet the nature of the links and the nature of the nodes are very different of each other. Now, so here is a small advert, right? So please don't feel obliged to buy the book because it's crazily expensive. If you're interested in it, just send me an email. I will send you the PDF. But so what I wanted to emphasize is the fact that among the questions that I personally and other people are interested in is to try to understand how, first of all, how the structure of a graph of a network affects dynamics. For instance, that would be what is the influence of the structure of the contact network on the way a certain variant would be spreading in the population, for instance. But then there is also another question that is quite important. That would be, is it possible to use dynamics in order to retrieve and to extract some important structural features in a graph? So is it possible to use dynamics in order to say, for instance, what are the nodes that are important ones? Is it possible to cluster the nodes together? That would be a field called community detection. And indeed, there are many methods that exist that use random walks, that use diffusive models in order to extract information from graphs. And something that is also quite important is to try to understand how is the structure of the graph itself evolving in time. It's a question that very much relates to this question that I just gave before. And that would be more specifically, how does the system respond to a perturbation? Now, as I said, I'm a physicist, and in physics, there are beautiful theories associated to something called linear response theory and basically response theory, where you basically can understand the intrinsic behavior of a system by observing the way it responds to a shock, it responds to an impulse. And this is something that is called linear response theory. From the response to a shock, you may actually understand the way the system behaves internally, and you can understand its statistical properties, basically. And this is the response theory is a beautiful theory that dates from, I don't know, like 70, 80 years ago, probably even older than that. But yet, this is something that has been used in all sorts of contexts, sometimes completely different from the classical physics background. And I just wanted to give you one example where, for instance, here, that this is a paper I was involved in with Michael Schaub, Jean-Charles Delven, and Mauricio Barahona. In there, what we try to do is to take a graph, right, and to try to assess whether or not two nodes are similar by putting an impulse on the first node, looking at the response that's associated to a random walk or a certain diffusion that takes place. You took another impulse on another node, you look at the response, right? And if you compare the responses, you're going to say that two nodes are similar if the two nodes tend to generate the same responses. So by comparing the responses of the impulses that you put on different nodes, you basically have a way to check whether or not the two nodes would be very similar. And here we did it in a way that is very much related to this response theory, but actually many methods from machine learning or graph analytics are somehow having these kind of ideas in their background. You can think, for instance, of random walk with restarts. That would be something that would be related to that. You can also think at node2vec, for instance, that would also be something that is related to what I'm saying here. But the most important thing is that there are many methods that exist that uses shocks, responses to shocks, and using the shape of these responses to try to extract information from the graph. Now here, what I'm going to talk about is not this. I will not take a graph, put a response, like impose a shock and look at the response of a diffusive model. What I'm going to be interested in is something that's a bit different. I'm going to be looking at situations where actually we make measurements, and we make measurements on of certain collective behaviors. And we know that these behaviors basically take place between agents, in a population of agents that are basically interacting with each other. And actually, it's a motivating example for this talk and for the rest I'm going to be talking about. I just wanted to emphasize a fairly old paper. It's a paper that I read actually when I finished my PhD. I was a PhD student in physics. I was doing some fluid dynamics, and then I moved to graphs. It was in 2004 exactly. And one of the first works that I read at the time was by Sornet and others. And I just found it fascinating. So it was a paper called Endogenous versus Exogenous Shocks in Complex Networks, an empirical test using book sale rankings. And basically what did they do? They looked at the way the sales of a certain book I don't know, you can, at the time, they must have looked, for instance, at Harry Potter, I suppose. You look at the sales of Harry Potter books, right? And clearly, if you look at the signal, what you will see is that there are fluctuations, right? And they looked, if I'm remembering well, at the sales from Amazon already at the time. So they had Amazon sales, and they looked at it on a daily level, and you would have fluctuations, obviously. And you have fluctuations that are just intrinsic to the system, right? Naturally, system fluctuates. But then what happens is that for certain books and in certain situations, you actually have that you would have peaks of sales and then relaxation, basically, right? And what they were interested in was to try to understand what can explain these shocks, right? And is it possible basically to characterize the relaxation after those shocks, a bit in the same spirit of what I said just before. And in this work and following works, they started with book sales, and then they looked at YouTube videos, a bit along the same vein. I think that they looked at a very nice combination of elements. So what they considered were agents interacting with each other and influencing each other. So for instance, if I buy a book, I might talk about it to my friends, right? Who might buy it as well. So it means that there is a bit of self-excitation in the process, where if I buy, I will excite others to buy something. And so they had models that would be reminiscent of something called Hawkes processes. For those of you who know, and Hawkes processes have been very popular, for instance, to model cascade in social media, much more recently in the last few years. But already then they looked at those Hawkes processes and self-exciting processes. There are these interactions between agents, and as well, they tried to understand the differences between shocks that would basically occur due to endogenous forces, just due to internal fluctuations. You would have basically suddenly the emergence of like trends that would basically disappear in time, versus what would happen in the situation where you would have an external shock. And this external shock, as was said before just by Martin, would be like going on TV, for instance, or might be the death of an author, and typically those would be the main ones, right? And the death of an author, or some like external, being on the news media for one reason or the other, leading to the shocks and then to the responses. And this is a very nice paper, actually. And actually, in the following paper, you can recognize the name of Sornet. So they looked, in this case, at like YouTube videos. And in that paper, what they tried to distinguish were two types of shocks, right? The first one on the left would be one where you would have a very rapid increase and then a decay. And that would typically be associated to a situation where you would have something external from the system, like going on CNN, or having the death of someone, or having something that is external that leads to increase of the sales, and then you would have like a relaxation coming after. That would be the one on the left. And they had the other ones that would be endogenous, where in this case you would have that there would be an increase that comes from the intrinsic interaction between all of the agents, leading to a peak and then to a relaxation just after. And what they could do in that work was to show the statistical differences that exist between these two different types of shocks, and trying to explain them with certain models and to compare the models with the data. So it was a very nice paper. Now, actually, a couple of years after, there were actually some very nice work by Lemon, where in that case, it was not based on a model, it was more based on data. And to be honest, I don't remember what was the data from. Was it on Twitter, I suppose? In that case, what they looked at was something very similar. They looked at the time evolution of certain hashtags, right? And here, what they tried to do was to try to classify the different types of peaks that they would observe in that data. And what they had were basically 4 families of peaks that they observed. One where you would have a gradual increase until you get a maximum at a certain time. Another one, there would be something where you would actually have like a shock and a relaxation. Then something where you have an increase, you go to a maximum, then you have a minimum, and then it decreases. And then something else where you just have like an event on the day and nothing else after, basically. And basically what they did in that case was to try to classify the different types of peaks and to try to find some interpretation for the for what it means, right? What would be the mechanisms that lead to these different types of like anticipation, as I will call it, after, and relaxation just after. But I think that nonetheless, in most of the research, and there have been many more other works after, most of the research has been focusing on what's on the left here, right? So a shock and a relaxation, like the one here, a shock and a relaxation. And this is something that where there's been a lot of work taking place. So I can think, for instance, the work of a colleague of mine, Taha Yasseri, and he looked at the way you would have like how the attention of people towards certain catastrophes would actually decay in the course of time. And he observed, if I'm right, that typically the time span would be of a matter of weeks before you stop to see like a significant signal in the attention of the users on Wikipedia, actually. But here we actually wanted to look at something different. We wanted to look at it from the left perspective. That would be what is the behavior of people when there is not a shock that is completely unexpected, but more we know that something is going to be happening in the future. There is a planned event in the future that might be an election, it might be a football match, it can be a film release. We know when this is going to be taking place, and we wanted to understand how does this anticipation lead to growth of the attention, and after the event, how does it decay afterwards? Now, in order to do so, what we did was we collected some time series of Wikipedia page views. We looked at hourly page views, basically, of a large number of events that were pre-planned. And we considered a bit more than 3,000 of those events that we categorized into 5 classes. One about elections, one about sports, one about football, one about film release, and one about holidays. And actually, if you want to know the story of this project, it's actually started because for some reason or the other, Ryota, my colleague, looked at the time series of UFC, which is this ultimate fighting club. I don't even know what it is. Well, this is this very violent version of boxing, right? And he observed these very regular patterns in the way the people would actually look at UFC pages in the course of time, and an increase that seemed to be very predictable. And that's how we started to look at it, actually, even if we are not big fans of that specific sport. And we basically increased the range and looked at all sort of classes of events. And here is an example, right? You have the 2016 NHL Winter Classic, which is like a sport event. It's known in the future. And here what we have is the way you have the time evolution of the time views until the event where you have a peak and then it goes down, basically. Now, here we basically had 2 research questions that we had in mind, and I'll try to be fast because I think that I'm a bit slower than I thought. The first, and the 2 questions were the following. The first one is, what are the essential characteristics of the temporal pattern towards planned events? And then the second one was, how is event-related information, such that the category of the event or the outcome of it, or how it got realized, affects the temporal patterns? Now, for the first question, what we built was a very simple model that we use in order to fit the time series that we had, basically. And what we basically had was that we considered 3 characteristics. One would be the anticipation, another one would be the response, and the third one would be the circadian rhythms. Because we noticed that clearly, because we looked at hourly data, it was quite important to include basically all of these circadian rhythms in the fitting procedure. Otherwise, the results that we had were very bad, actually. And actually, by doing so, we had a certain number of parameters, certain that would be associated to the to the phase of our oscillations. Of course, the period would be 24 hours, but we also had like something that would be associated to the characteristic time of how fast you go to the maximum, the characteristic time of how fast you decay after the event, and also something that would be associated to the what would be the baseline level before and after the shock, and also what would be the amplitude of the shocks before and after, basically. And so we had here a certain number of parameters that we used basically to fit the data that we had. And if we did this, so here are just a certain number of examples where actually the procedure, well, of course, we have a certain number of parameters, but they're all quite interpretable. And actually, it can give us extremely good fits in general to all different types of patterns that you observed, having things like those, right? Like the film Gringo, where you have something that is very symmetric and clearly the oscillations are very important and well defined, to something that would be like a holidays, where there is a lot of anticipation and then almost nothing after it, or something related to sports, where in this case, well, this is the Boston Marathon, where we know that something extra, well, like a very catastrophic event took place on that day, and where in this case you would have a peak, and then the relaxation is actually much more important than the anticipation. Now, the thing is that what we then try to understand is that, okay, so we have a good fitting procedure. Now, what we wanted to understand is how does the category and the outcome affect basically these parameters that we fit. And the first thing that we did was to look basically at different types of events. And so we have many events, right? Each of them is basically measured by, is characterized by a certain number of parameters that are the model parameters that we fit. So it means that each event basically can be embedded in a space, right? That would be 1, 2, 3, 6, 8-dimensional space. And then each of these points are together. And then what you can do is to basically do a clustering in that space. And we did it with Gaussian mixture model, which is a classical technique, with BIC, which is Bayesian information criterion, to determine the number of clusters. And by doing so, then what we did was to find clusters of events, right? And what we observed is that actually, if you look at like the cluster 1, for instance, it's mostly made of sports events. Cluster 2, it's mostly made of football events. Cluster 3, mostly made of film events. So it really seemed like clearly the category of the event is very much related in this unsupervised classification problem that we had to the nature of the event itself. And this led us to look at a second problem that would be more predictive now, where actually what we did by using some Bayesian techniques to try to predict what will be the future course of the views of an event by using the parameters that had been fitted before the event, right? Plus the category itself. And here what we observed is that we got actually an accuracy that was much, much, much better than the one that we would have had otherwise. Meaning that if you want to predict the response after an event, well, knowing what's happening before and knowing what type of event you're considering can really lead to very nice improvements for the predictions that you have for the response after it. And just 2 more slides, don't worry. The next thing that we did, and this is something that we did, but could be explored further, is we observed actually something that is quite funny, is the fact that, so for instance, if you consider some football games, and here that would be Manchester City versus Liverpool, what you observe is that if you plot the views of the Wikipedia page, clearly you observe that you have a persistent activity, but also a relaxation that is much slower in the case when you would have a win instead of a lose. Meaning that clearly the outcome that we have and the reactions that are triggered after the event clearly depends on who's going to be the winner, right? And here in this case, well, the winner is remembered while the losers will be forgotten, according to a sentence by Jürgen Klopp, who's actually the trainer of Liverpool Football Club. So, okay, so let me conclude, and I hope I was not too long. So here, what was our purpose? Well, me as a researcher, I was very much interested in these response question, right? How does a system respond to something? Except that here, the response was anticipated. We wanted to understand how does the system basically anticipate something when we know when it's going to be taking place in the future. And the way that we did was to collect data from Wikipedia, to consider different types of events, to have a model that would allow us to fit the curves that we observed empirically, and then basically to use this methodology in order to try to make sense of the different types of responses based on their anticipation and also on the nature of the event itself. And having said that, well, I think that I arrived at the end of my presentation. I hope that you enjoyed it. And I look forward to any question if we have the time and if you have any question. Thank you very much.
Thank you so much, Renaud, for this presentation. I hope you're around for some Q&A. We do have time for questions.
Yeah.
Yes. So just as an announcement, if you have questions for Renaud, please put them in the chat on YouTube or IRC. We relay them here. If there's let's start with questions in the room. Anyone wants to go? Diego, I see your hand.
Yeah, Thank you, Renaud. That was a super interesting presentation. My connection was dropping a bit, so sorry if I asked something that you already mentioned, but one thing that is very interesting for us is to be able to measure, to predict the impact that a given event will have in our platforms, especially if you think in event that could be related with disinformation, for example, some election or some political event. For us would be super useful to try to predict across different projects. So let's say an election in some country could have impact in that specific language of Wikipedia, or I don't know, social movement, something happening in one country can have impact in this other language. So to be prepared to deal with such situations, for us is very important to be able to predict what will be the specific impact of that event in a specific language community. Do you think that what you show here could be used for in that use case, let's say?
I think, well, potentially, well, of course, that should be improved. Well, it should be improved, I suppose, or at least like fine-tuned for your specific application. So some random answers, and I hope that among those that I give, one is going to be the one that you look for. The things that, first of all, something that would indeed be quite interesting is also, because here we just look at the consumption, right? We don't look at the way the pages are edited as well, right? And something that might also be like a good signal, especially if you're interested in disinformation, would be to try to figure out also what's happening in terms of the edit wars, right? And the conflictual edits that take place before an event takes place, which might actually be like a precursory sign of potential conflicts, and then enhance possible misinformation that might be taking place inside the community for one specific event. So it means that potentially what we do here could be generalized in a way with respect to edits, and maybe contradictory edits that takes place ahead of an event that takes place in time. That's just one thought that I have. And another thing is that indeed something that would be nice is to potentially, because here something that we try to show is that the nature of the event, right, and the realization of the event seems to be associated to the time series before and after the event itself. And so it means that it might be nice to see if it's possible to build a corpus of data of events that are known to be associated to either like misinformation in a broad sense, and to see if methods like those can help to basically identify them, right? So it means that, is there something specific in the signal that can help basically to identify them, either ahead of it, that would be wonderful, but even, or also just after it, right? So that's indeed, this is something that could be actually spotted and identified by the Wikipedia community. And the other thing that might be related somehow is the fact that, so here indeed, we look at all of the pages independently from each other, right? And I told you that I'm someone interested in networks. Here we don't use many networks, right? We just know that there is like underlying everything, there is a population of people interacted with each other, right? So I know that there is a network somewhere. I also know that there is a network in the Wikipedia itself. But what I wanted to emphasize is the fact that something that would indeed be interesting is to look at the way certain peaks in certain pages affect the other pages, right? And actually, this is something that Patrick had been investigating. So he has a paper that's been submitted, not accepted yet. So hopefully he might be someone who could be giving you a nice answer in the future. Just send me an email and we can share the paper with you if you wish. And I gave 3 answers. I don't know if you gave if any of those was the one associated to your question, but I tried.
No, thank you. It was very interesting, and I'll write you an email later to follow the discussion. Thank you very much.
No, thanks to you.
I would have a follow-up question, Renaud, that these results that you show I find very impressive, and the potential application that Diego describes, I think, would be very, very important or very worthwhile. So my question is around other there's Wikipedia articles does not just relate to these types of events, even though we know that many of the high or most viewed articles actually fall into these types of categories. So I was wondering if you have some insight about other types of categories or event categories for which you perhaps excluded or not, because maybe there's some intrinsic limit to the predictability, or where you see kind of intrinsic limitations that where you already think this should not work, or maybe other cases where it should work even better. I would be curious to, even if you didn't do research, what are your thoughts on that?
No, the things that, so of course there's a little bit of pre-processing that have been hiding under the carpet, I suppose. So the things that clearly, and because just to give you like a broad overview, so with Ryota, who's my co-author here, we've actually been interested, well, the both of us are interested in situations where the data is non-stationary. And so I'm a methodology person, so I find it interesting when things are complicated, I suppose. And so actually we started the collaboration more with Twitter, like it was 2 or 3 years ago, or 4 years ago actually, looking at like the way tweets would be retweeted, right? And trying to see if you have a tweet, if you have the number of retweets for the first 2 hours, how can you predict what's going to be happening in the future, right? How can you predict the size of the cascade in the long term? And actually there we observed as well that we needed to incorporate these periodicities, these like day-night basically oscillations, in order to get fairly good models. And we had a model that was some sort of like a self-exciting model, but where we incorporated daily oscillations basically. And that's how we basically arrived to this project in a way, trying to even if the methodology is quite different, we still had these kind of like oscillations in mind. But nonetheless, it also means that in order to fit them, and I know that for the retreats, we could only look at the large cascades to do the predictions. Well, clearly here we also need to have sufficiently good signals for us to have a build-up towards the peak. And I forgot what was the exact threshold that we used, but we used a minimum number of views as a way to filter out what would be the important versus the less important event. And actually, we didn't do it on purpose, that we chose a threshold that was such that we optimized the quality of the predictions. We just took something that was realistic for us, at least, and then it seemed to work well. But clearly, if you are to go to situations where there are less events, less important ones, especially maybe like more surprising ones, then clearly what we have here would be much less accurate, I suppose. And we didn't really try to go in this direction. And actually, it somehow contradicts what I said for my first answer. Because actually, I would expect that for the number of edits, you might have less edits than views. Or maybe I'm wrong. Actually, maybe I'm completely wrong. But maybe there's actually in situations where you look at the edits where the data might be more sparse, then some of these methods that we have here might be a bit more tricky to fit. We have 8 parameters. It's not so much, but still 8 is more than 2, right? So it means that, yeah, so we need to have a sufficient amount of data for the fitting.
Thank you. I think we have questions on YouTube. Emily.
Yes, we have 2 questions from YouTube. So the first one is, do you think that you have discovered all of the different patterns in page views, or do you think that there are new patterns that are yet to be discovered?
Well, the thing is that it's always a question with clustering, right? So I'm coming from, well, one of my contributions to, well, my main contribution to science, if there is one, is a way to do some clustering. It's a clustering technique basically, and we know in clustering that finding the right number of cluster is always a very tricky problem. So here, what we did was to use this BIC, and this is a classical one. But in any type of data, you can always argue that the number of clusters that you have is not the right one. So I think that it makes very much sense to consider, well, to have these 4 clusters that appear, right? Anticipation, response, a bit of both, and something that would be very peaked. These seem to be the most canonical ones. But then I'm also pretty sure that if you were to have more data, it might be possible to find among these groups, maybe subgroups, right? Things that are like, so it means that there's always a way when you do some unsupervised clustering to find a way to divide big cluster into smaller clusters. But I think that those 4 ones that have been found, not by me, right, by Lehman and by people before me, I think that they make very much sense, and I think that they are probably the main ones. And then after that, there might be ways to do some subdivisions among those, but those would be, I would presume, the 4 most important ones, and also very intuitive to understand.
I think we can take one more question. Is one more question before switching to Christina? Emily, is there another one?
Yes, we have one more question from YouTube. Is it possible to identify articles that have these patterns, these peaks in page views, without having selected the articles yourself?
Well, actually, we didn't try that. It's a good question. So it's true that here what we did, we only picked. So actually, okay. So in some of the papers, so maybe that's people have done that. I don't know. We didn't do it. So in our case, we only looked at papers where we knew by definition that there would be a fixed date in the future, right? And so if I understand correctly, the question is, if you look at the patterns, right, is it to predict that an event is pre-planned in the future, right? That would be, and that could be an interesting research question. So I would expect yes, but I would expect that with a fair level of accuracy, you could predict yes or no if there is going to be an event. You might actually even predict possibly when it's going to be. So yeah, different types of prediction tasks that you can think of, right? Classification. Is it going to be one with an event that is planned in the future or not, right? That would be one way to look at the problem. The other one would be, is it possible to predict when the peak will happen? That might also be one that would be an interesting one. And but I don't know the answer. So please, the person who asked the question, if you want to try it and to give me the answer, I would be more than happy to hear what you discovered.
Thank you so much for these answers. Renaud, thank you for your talk. I think we'll close or stop the discussion at this point. Maybe we can, if you're able to stay around, or
but I will disappear for some time and I'll try to join later. So so actually I'm jumping in the car just in 2 minutes to but I hope to be back.
Thank you so much. And
thank you. And yes, and looking, I hope the next talk goes well.
Thank you. And if you have other questions or follow-up questions, please put them in the chat. We can revisit in the next Q&A. And with this, Christina, our second speaker, please.
Okay, can you see my slides?
Yes, we can see it.
All good. Okay, thank you. Thank you so much for hosting me. I think this is a super fun session, and thank you also for his talk, although he just left. I find the work that I will talk about very related and yet complementary, because it concerns the COVID pandemic, which we can see as an exogenous shock and completely unplanned, as opposed to these more kind of planned events like such as elections and football matches. So, hi everyone, my name is Kristina Gligoric. I am a PhD student at EPFL, and I will discuss our work about sudden attention shifts on Wikipedia during the COVID-19 crisis. This is joint work with Manuel, Maxime, and Bob from EPFL, and Florian and Marcus from GESIS. So just to give you a bit of background on this project, we started working on this project in March 2020, seeing how COVID-19 pandemic was leading to implementation of really unprecedented interventions, including full-scale national lockdowns. And clearly these interventions have created massive shifts in people's lives. So in May 2020, more than a third of the global population was under lockdown. And clearly COVID-19 was met with immediate efforts to understand the virus, to understand the disease that this causes, to understand its spread. But the premise here is that many of the challenges related to this crisis come not only from the virus itself, but also from social, economic, and psychological implications of the implemented measures. So because of that, we argue that there is a need for broader research efforts that would aim to identify how the pandemic has broadly impacted human needs, interests, and concerns. So, however, it turns out that if that is our goal, to quantify the impact of COVID-19 on interests and needs, there are certain challenges. So if we want to use traditional methods such as surveys, the first challenge is immediacy. And immediacy relates to the fact that if we send out surveys to people around the world, we need to wait for people to fill them, and then we need to analyze the results. But COVID, so the pandemic is an ongoing crisis where needs, interests, and concerns are dynamic, and there is the need for immediacy, and we cannot wait for that kind of delay. The second challenge of these traditional methods relates to the need to scale up our analysis globally. So we need to, COVID-19 affected people around the world, and due to its global nature, our analysis aiming to understand human behaviors also need to scale globally. And both immediacy and scale are something that is challenging for the more traditional methods. So in our goal of identifying how the pandemic has impacted human needs, interests, and concerns, we turned to Wikipedia. So fortunately or not, unlike most of the previous events that impacted so many people around the world, COVID-19 pandemic developed at the time of widespread internet access. And Wikipedia, the world's largest encyclopedia and one of the most visited sites of the web, captures rich traces from its readers. And these traces are also publicly available in aggregated form. So in that sense, Wikipedia allows us to characterize attention shifts in a systematic way due to its nature. So first, it fulfills the need for immediacy because it is always on. And then second, it lets us do so at scale since it is globally and freely available with versions in languages spoken all over the world. So before starting this project, our hypothesis was that in times of uncertainty, people around the world would turn to Wikipedia for information. So people might focus their attention on, for example, articles related to the nature of the disease, but also on the rest of the Wikipedia, because the information not related to the disease can still be of increased interest to people around the world. But then also people might be interested in everything in between, where concepts related to the pandemic, but not directly to the virus, might be of increased interest. And here I just wanted briefly to outline that our work was really inspired and aims to extend a rich literature that studies these kinds of behavioral changes of Wikipedia readers during unexpected events, crises, diseases, catastrophes. So previously, researchers used Wikipedia page views to monitor and forecast diseases, including influenza, H1N1, and the Zika virus, just to highlight a few studies. So in that sense, studying behavioral changes of Wikipedia readers during the unexpected events is clearly a very, very active research area. And this was a starting point for our work. So the key idea here is to use Wikipedia page view data to understand how information seeking behavior changed during the pandemic, and to try to quantify it in a systematic way, So in the language of the previous talk, this would involve disentangling the exogenous shocks from the endogenous trends and fluctuations. Okay, so to do so, we analyze Wikipedia access logs in 12 language editions of various sizes, and we analyze the time frame between January 2019 to July 2020. And the analysis I will discuss here are limited to the first wave of the pandemic. So this is something to keep in mind. And then for each language edition, we obtain publicly available page view statistics, which specify how frequently each article was accessed daily. And we also aggregate the desktop and mobile versions of the site. And when choosing language editions, when we chose these 12, we considered the size of the edition, whether the language was spoken in relatively few countries, and also the kinds of non-pharmaceutical interventions that were imposed to cover the spectrum from the strictest to the mildest. Then next, our analysis combined Wikipedia access logs with mobility reports, which are made available by Apple and Google. So these mobility reports capture population-wide movement patterns based on phone location signals. And then the reports specify for each day what percentage of time spent in various location types, for example, residential areas or restaurants or workplace, differs from pre-pandemic baseline. And the premise is that both government mandated lockdowns as well as some self-motivated distancing measures would show up as sharp changes in mobility time series. So then we detect automatically these changes in mobility patterns using change point detection algorithms. Another challenge here is mapping Wikipedia language editions to regions, because there are languages that are spoken in multiple countries. So then for such languages spoken in multiple countries, such as German or English, we average mobility time series from the main countries where the language is spoken, and we weight according to the proportion of native speakers. Okay, so then back to page view counts. So let's consider an example of Italian Wikipedia. So we focus on the temporal evolution in 2020. So on x-axis, we have time, and we monitor page view counts on y-axis. We monitor the total number of page views, and the first thing that we see during 2020, a lot of temporal variation. We see that the page views roughly doubled in April compared to March. However, looking only at 2020, these could be some normal seasonal fluctuations or some special external events that occur every year and that might not have anything to do with the pandemic. So to account for such external factors, we consider the page views in the previous year, in 2019, as a baseline, shown in green. And then in order to quantify the effect of the shock of the pandemic, we isolate the mobility change point. So this is the moment in time when mobility drastically reduced, when people started to spend a lot more time at home. And another important moment in time that we consider is what we refer to as normality change point. So this doesn't represent abrupt change in mobility pattern, but rather maps to the time when mobility returned to normal. And these times are also calculated with mobility data by identifying the time when future average mobility remains within a baseline level. So this is related to the shock and the relaxation that Renaud mentioned. So in that sense, here we want to see what happened with attention once mobility time series finished the relaxation and returned back to normal. Okay, then we also explored 5 important dates that are marked here in pink for Italy. So the 5 dates are the first reported case of COVID, first reported death, the ban of public events, the date of first school closure, and the date of lockdown. But I won't go into too much detail here for simplicity. I will discuss analysis studying the mobility change point, but we can apply the analysis framework on these dates as well. Okay, so remember, our goal is to identify the impact of COVID-19 related events on page view counts. However, we need to disentangle these kinds of trends and seasonalities from COVID-19 impact, and we try to overcome these hurdles by performing difference in difference regression analysis. The key idea is the following. We monitor the page views on y-axis in the period before mobility change, and we contrast them with the page views in the period after mobility changed, but in 2019. So this is before the pandemic. And then due to fluctuations and trends, these two are not equal, not even in 2019, before COVID. Then we consider page views in 2020 in the period before mobility changed. And we make a prediction about the expected value in 2020 after mobility changed based on the trends in 2019. But if there is an impact of mobility restrictions, the page views in 2020 after mobility changed diverge from this counterfactual prediction. And this difference in differences is the quantity that we are interested in. By how much did interest change after mobility decreased, controlling for the pre-pandemic fluctuations. This is the main idea and the main framework in which we analyze the page view count. Okay, then by modeling the relative increase in a multiplicative model of the total number of page views, which we have on the x-axis, in different countries, which we have on y-axis, our analysis can show what was the impact of mobility decrease. And what our analysis show is a sharp increase in the volume of Wikipedia usage by up to 40% following the sudden decrease in mobility. The strongest in Italian and Serbian language edition, and the smallest in Danish and Swedish, which maps the intuition that Italy and Serbia had very strict mobility restrictions, whereas Sweden and Denmark were on the less strict side. Then we can repeat the same analysis by contrasting periods before mobility changed and after mobility went back to normal. And here the idea is that contrasting these two periods instead lets us measure more long-term effects. Once we do that, we can see that the increases in page views were transient. In the long run, there was either a decrease or no significant increase in 11 out of the 12 languages. So for all languages except for Serbian, the overall page views went back to normal as mobility went back to normal. And here we can speculate regarding Serbia, whether there was some kind of permanent shift in readership of Wikipedia, or maybe mobility time series actually did not reflect the state of the crisis, since the lockdowns were lifted, but the case counts remained high. So maybe a normality wasn't reached yet in the case of Serbia. Then to gain further insights into which kinds of articles people were reading, we enriched our page view data with ORES, a tool which we use for automatic categorization of Wikipedia pages. So we labeled each article with one of the 57 topics, and this lets us really zoom in on what kinds of article received more or less attention throughout the pandemic. Okay, so let me unpack these results. Again, on x-axis, we have the relative increase in the page views pulled across the 12 languages. And then we monitor separately short-term effects on the left and long-term effects on the right. And we group topics by the type of change that they experience. So first, we can see that some topics, for example, biology, but also literature, television, films, and entertainment, saw transient increases. So initially there was an increase in interest, but then as mobility went back to normal, the interest in these topics also went back to normal. On the other hand, interest in some other topics permanently increased. So it increased after mobility changed, but then it remained increased even when mobility back to normal. And in this category of topics, we have video games, books, internet culture, and fashion. On the other hand, interest in some topics decreased, the decrease being permanent, such as in sports, which really makes sense because during 2020, there were no sports events. And then finally, there are some topics that saw transient decrease. So there was decrease, but then it went back to normal. And here we have transportation. So surprisingly, overall, many of the topics with persistent increases relate not to some basic needs related to the pandemic, but to entertainment and self-actualization. So here we have video games, books, internet culture, fashion. And we believe that this says something about how people responded to the COVID pandemic. And other topics among the 57 that are not listed here remained unchanged. Okay, I think I will try to wrap up. I'm not sure what is the time status, but okay. So I wanted to highlight 3 main takeaways and to try to kind of digest the analysis that I talked about here. So first, we hope that our findings may help in characterizing the societal impact of the pandemic. These trends in volume of page views themselves can be interpreted as a trace of the social impact of the pandemic. And the picture that emerges is that the increase in information seeking that followed mobility restrictions relates to fulfilling needs that we were deprived of due to closures. So in that sense, Wikipedia is really an important source in the time of crisis because it provides crucial information to millions of people. But then second, things do not stop there. Wikipedia also plays a role in providing information related to non-essential needs. So the topics that experienced persistent increase, such as video games, internet culture, are not related to needs that we would think of as basic, but rather relate to people's need for entertainment and self-actualization. And then third, our analysis also suggests that at least within the studied time frame, the societal impact of the crisis persisted beyond the mobility restrictions. So this acts as evidence that these kind of long-term changes induced by the pandemic are not only geopolitical or economic, but also relate to what humans need, what we are interested in, and what are our concerns. And then finally, I wanted just to briefly touch on future opportunities. I'm also curious about any questions or suggestions. One thing that we were thinking about a lot is thinking a bit outside of the COVID pandemic and thinking whether we can, instead of characterizing how COVID impacted our attention, can we use COVID as an instance of a crisis that would let us learn something general about human behaviors? So for example, can we treat COVID as an instrumental variable that nudges people a bit to stay at home, and then use that fact to understand, for example, what books people read when they stay at home, what dishes people cook, what hobbies we engage with when we spend more time at home. So these are some ideas. And thank you. I'm happy to take any questions.
Thank you, Christina, for this talk. We have time for Q&A. If you have questions, please put them in the chat, and Emily can relay them here in the room. I would start with one question, which is about, you saw a big impact from mobility restrictions to page views in Wikipedia. My question is around these mobility patterns in general. I don't know how stable they are in non-pandemic times, when there's no pandemic, when there's no restrictions, if these mobility patterns also change, and if we would also see something like this in a non-pandemic time, that if people are more mobile in general, we see more people going to Wikipedia to read information. I don't know if you know anything about that. I know it's not part of the paper, but I'm just curious because I don't know much about this type of data.
Yeah. That's a good question. So from my understanding, these mobility reports are always given as some kind of in reference to some baseline, and the baselines usually capture, for example, weekly variation. So in that sense, they're very handy to study impact of these special dates during the pandemic. It's just that the COVID shocks were really, really large. So then those show up really, really clearly in this series. But outside of COVID, I agree that it would be super cool just in regular times to correlate the attention on Wikipedia with the mobility time series that do have the natural fluctuations, the weekly fluctuation. I am not sure. So for example, it would be really interesting to see during a day, like to correlate like for each hour during the day, what articles we are reading and how we are moving. But these reports that we worked with are not made public in hourly granularity. But I think it would be a really cool research direction to search for these kinds of mobility data that would let us do that. Because then we could see, for example, when people go to work, like when people leave home and go to work, and then how topics that they read change from entertainment to work related. I think that, yeah, it would be feasible.
Thank you. I think, Diego, you had a question.
Yeah, thank you very much for the presentation, Christina. It was super interesting. I called my attention this last use case that you mentioned, and you mentioned a bit more about this now in your last answer. What do you think could learn other platforms, not Wikipedia, from this, and what do you think would be the ethical/privacy implication of this? Because, for example, Google knows all this information already. They know when they know in many cases, like your GPS, your position, how you're moving. Internet or phone providers knows this information too. Their data sets with towers and the time of and the page that people is connecting. There's studies around that. Do you think that this approach that you're suggesting could help to make that kind of work more privacy friendly, or what do you think are the ethical implications, and others that are working already with much more granular data can learn from this, and how you compare your results with that?
Yeah, it's that's something that we've been thinking about a lot. So there are already many studies using different kind of traces, like internet traffic, search logs, and then trying to identify what is the impact of mobility or COVID. And clearly there is a trade-off between what we can figure out about human behaviors and how that can be useful and empowering versus the privacy risks. And I think in my view, very aggregated population level analysis, such as the ones that I presented here, can be very useful and not particularly risky, even if done with other data sources that are maybe more sensitive. But as long as they are population level, so then that would mean, to refer to your point, how they are very granular. We should ignore the granularity in terms of users and not do user-specific analysis, but very granular population level analysis. So it would be really cool if we can do population level analysis that are granular in terms of time or small regions, but still population level. So I think that is something very valuable. But then if we try to infer exact individuals and what is the impact of events, even the planned ones, like from the last talk with elections or football matches or shocks like COVID, when we start to analyze individuals, a lot more privacy risks and tricky considerations emerge for sure.
Thank you very much for the answer. Continue the conversation later. Thank you. Sorry, Martin, go ahead.
Oh, you want to, if you have follow-up questions, then let's go to YouTube if there are questions.
Yep, we have one question from YouTube. How did you choose which languages to examine?
Yeah, I tried to briefly touch on that. So we wanted to have kind of like a diversity as much as possible in terms of language size, the nature of the mobility interventions that were implemented, and the extent to which a language is spoken only in one country. So this list of 12 languages was an attempt of a trade-off in those dimensions, given our resources and logistical restrictions. So yeah, that was the idea, to have countries that range from like Sweden and Denmark all the way to Italy and Serbia in terms of how strict the lockdowns were, to have bigger language editions like English and also smaller like Serbian or Korean. So yeah, trying to navigate that space.
I have a follow-up question on that. I really liked the fact that you looked at the different language editions and how the impact was different in different regions of the world. For the topic analysis, was this when you described which topics received more attention or less attention? Was this, I assume this was an average over all the languages you considered, and whether you saw some differences there in different countries or the different projects?
Yeah. So the analysis that I presented were, the topic analysis I presented were pooling across all languages. So it was on average in that sense. We did examine the topical shifts separately for the different language editions. And I remember that we saw some interesting patterns, but we didn't investigate those too much in detail because we wanted to give like a global overall picture that was emerging. But yeah, if I remember correctly, in countries that were in countries that had striking case counts, such as Italy, that was reflected in the topics that had the biggest shifts.
Great. I think with this, there are no more questions on YouTube. We are also at time. Actually, we are way over time. So that is a perfect moment to wrap up. I want to thank Christina and Renaud, our two speakers today, for their excellent presentations and sharing their research with us. I want to thank everyone who joined us today, and thank everyone for the discussion we had here. That was really interesting. And I also want to thank for the technical support from Emerald so that we can have these live video presentations. And with this, I wish you a good rest of the day, and hopefully see you in as well in the next month's research showcase. Bye.